environment that lets you kind of do interesting calculations on the cloud, on clusters, on-prem systems, and any kind of devices you have right from your Python setup. So just to take a stock over here. So how many of you people are familiar with using in high compute, either on the cloud or on-prem or on your laptop, wherever? Oh, okay, cool. Do you guys use in GPUs for ML training or anything of the sorts? How many of you are familiar with that? Perfect, awesome. Then this is a right set of audience for us coming in. Okay, so just to start with, let me set the stage for why we think there needs to be a new way of looking at such tools coming in. Just a decade ago or something, you had this entire transition of cloud era coming in. So people from on-prem systems started moving things to the cloud. And that instigated a new set of tools that needed to come in. And you can think of tools like Kubernetes and Docker that facilitated this transition moving in from on-prem to cloud setup over there. And then half a decade or so ago, the big term was the big data. So that involves collecting large data and handling it and working around with such kind of data coming in. And again, new set of tools came in for that. Examples are Spark, Hadoop, you name it. Of course, every one of you is an expert over here in big data. So all those set of tools coming in. And then the current set of era, what we call as compute era, came in and mostly driven by the needs of large compute that is needed for either machine learning or compute needed for niche set of things, writing from FPGAs to ASICs to GPUs to even quantum computers that we do work with as well. So these kind of new systems are coming in and new paradigms are coming in, and there exists no such tool which is dedicated towards accelerating compute and facilitating this compute speed up. And this is very critical because it comes in with its own challenge that you need to solve in. A good example of that that you might be familiar with is the lack of GPU access on the cloud. So if you want to access H100s, let's say, or even A100s on GPU, you need to wait a long time in the queue. And typically Kubernetes and other things won't handle large queues. And these calculations may run in for a couple of days or hours together, while Kubernetes or Docker are meant for things that are more IO bound, more scaling apps and those kind of setup. And people typically in the academic side are familiar with these kind of high performance tools. And one of the example is, let's say if you have worked with Slurm schedulers, PBS, LSF, these kind of schedulers are truly maintained for running in high performance jobs with large queues, large time to access. But these don't exactly translate into a Pythonic world or a cloud world. These are more typically meant for running in jobs in national labs, huge clusters, and those sort of things. So our way of thinking about this to come up with these kind of, to solve these kind of problems in with new tools that is more native towards what the language that people use, which is Python. And that's where we came up with this open source tool called Covalent on our side. And I let Radha introduce what exactly Covalent is on its end.
Okay, hello. I hope everyone can hear me okay. So like Santosh said, Covalent is an orchestration tool for high compute. And what it does for you is it connects you to any patchwork of resources that you have available to you in a really convenient and generic way right out of your own Python environment. So if you have access to AWS or Google Cloud, and even if you have some sort of GPU cluster or a Slurm cluster on the side, as long as you have the credentials to get into those things, there's a way to unify all that with Covalent in a way that's super convenient for you to use and super modular. So you can swap out different tasks going to different places, et cetera.
Just to add on to it, at any point, this is a tutorial, not a talk. So if you have any questions or feel free to interrupt us any point. And you also see a quantum computer over there, so we do connect to quantum computers as well. So if that's a point of interest for you, get in touch with me and I can talk more about it. Go ahead, Radha.
Yeah, and a big sort of selling point for Covalent, although we're talking about the open source version for now, is just the heterogeneity. So no matter what sort of resource you have in the back, you can plug it into Covalent and work with it in a lightweight and convenient way. So you can do CPU jobs, GPU jobs. If you're using quantum, you can also get into QPUs, and it's all unified in one place, and that place is Covalent. The last point down here, Covalent Cloud, is our fully managed offering, which is based on the open source version. We'll get into that towards the end of the presentation more. But for now, we'll take a look at just open source Covalent, what it's like to work with it, and some of the stuff that it can do for you. So here's maybe a first look at what the user experience is like. So you can see we have a little decorator that's denoting this train SVM function in this case as something called an electron. That's just the word we use for tasks. And when I say Covalent is convenient and modular, we understand that we can pass this electron something we call an executor. In this case, in this little GIF, it's just passing a string, so it'll be the default config that you have for any one of these platforms that you see it cycling through here.
Yeah. So just to add on to it, what this does is essentially you have a function that you want to ship it somewhere. You can test it locally. Say you just have 10 data that you want to check it locally in your laptop, you can do it in. And once you're fine with it, you can pass this function to any kind of compute backend on your end, be it AWS EC2 instance, batch instance, on-prem Slurm cluster. You have an access to SSH machine on your system with SSH credentials. You can just pass it by passing on your executor. This will exactly take care of packing your inputs, packing your functions, submitting it out there, calculating the outputs, storing the output in a metadata, getting it back, and everything that happens in the background for you without you doing anything on that side.
So, oh, this used to be white.
Oh, yeah.
I don't know what happened to my title there.
Okay, this says customize executors to run tasks wherever.
Yeah, it's a little bit more fleshed out version of the GIF back here. You can, of course, customize the execution environment as well. So if you're working with AWS Batch, you can specify the resources you want, the time limit, and as well as any dependencies that your task might have that you want to be available in the VM that actually ends up running the particular task. This thing on the right is just an example with a different executor. So in this case, maybe you're targeting a Slurm cluster somewhere, and you have your credentials, but also like the sort of the options you would see in a Slurm script. You can specify here as just parameters in a dictionary. So what you would do with both of these things is, like you see down here, you just pass this object to the decorator, and that will make your task run on the executor that's specified by that object. Man, I've lost a lot of text here. I'm going to make that white. Guess something happened when I pasted it into the... Oops. There we are.
Okay, so just to kind of pitch on a point on, for this current audience, where would Covalent be useful, as the title in the tutorial suggests. And so essentially, one of the major use cases that we have seen people using Covalent for are twofolds. One is essentially using Covalent as a backend for any kind of high-performance app that you write in. So if you need in your app any kind of GPU compute or CPU compute or any intensive compute that you need to have it in, and you need to write your code in a way that it's agnostic to the backend or the compute backend that you're sending it to, be it AWS, Azure, or GCP, or any kind of system. So you write your code in Covalent and you just tag along it, and you can scale it up or scale it down how much ever you want and send it to any kind of compute if you're using Covalent as a backend for your compute. So the setup that people typically have been having is shown over here. So you have your application code that sits over here, which is, I guess, anything that is being LLM or generative AI or any kind of application that you want to write in. And you essentially decorate that functions with a single line of decorator, and it ships it off to Covalent to compute and use any kind of compute backend that you need to do. And the entire orchestration is abstracted from you on your end while you're writing the application in. So this essentially splits the work, if you have a team, into two sets of things. One is the researcher who actually, or the data scientist who actually develops the code in, and the platform engineer essentially just slaps along a decorator on top and say, hey, I need these to run on AWS, I need these to run on GCP, or wherever you want to swap it in. And one of the pretty neat and interesting thing is that we have plugins, and this way that you swap in the executor is via a plugin system, so you can write your own plugins as well. So we have seen people write in plugins to GPU clouds that exist in all GPU clouds that give you very cheaper access to GPUs, like 50-90% of the cost that you would get out of typical cloud providers. So to connect to these guys without changing your actual business code is pretty useful, and that's where we have seen most of the people using Covalent for on this side. And the second use case that we have seen is moreover to the moving on from the production app to a more research phase happening in. Typically, while researching a lot of training in model and other things, the setup that you have is you write a Python script, you write a shell script if you're doing it on-prem to send it somewhere on an SSH machine or wherever you're sending it in. But you open up an EC2 instance or a VM and then submit your script, run your script, wait until it trains, and then see if there are any errors, and then redo it, iterate it, and do all those sort of things. So where Covalent helps in is that even when you're researching on your side, from Jupyter Notebook, you just slap along, once you're done it locally testing everything, slap along a single decorator, and it ships it to the cloud for you to do the compute in. And as Ara will show, we have a live monitoring UI that lets you monitor the code as it runs in live. And you can cancel it, redispatch it, swap it, change parts of your module and anything you want, right from your local laptop, and all those changes will reflect back in the cloud environment that you are working on. So that lets it pretty fast to iterate your research code throughout without even interacting with any kind of AWS console or GCP console or anything you have in your hand, or even without writing a single line of script on your end. Alright, so this is whenever we talk about Covalent, this is a slide that people usually ask in, like, why do I need to use Covalent instead of A, B, and C? So this is where we fit in. So to give a broad overview of this, again, going back to the chronological era, decade ago or something, parallelization was pretty important. And you had these kind of tools like, Joblib, Cython, Numba, and PyCode. And the goal here is to you're given a single PC, and you want to distribute your code throughout this multiple core system coming in. So that was the main motivation for these kind of parallelization tools that comes in. And then you had these distributed computation tools. So the goal is not only to have one PC with me, I have multiple PCs with me. And now I need to distribute my code throughout these PCs and work around with it. And then you had these tools like Dask, Rapids, Ray, and all those really nice tools over there. Putting a pause on going to the topmost tool, then you had your goal was not only to distribute these things, but you need to run it in a periodic order, and you have to combine these data pipelines to make very complicated workflows coming out of your system. And typically these things run in the cloud in production environment, things like running it in Netflix recommendation system, or shopping recommendation system, and those kind of things. And then you had these workflow tools that came in, like Prefect, Dagster, Airflow, Luigi, and all these really interesting tools. And where we sit in the stack is distributed workflow setup. So our intention is to have a workflow, but it's much more geared towards compute in the sense that each part of your task is indeed a compute intensive or not so compute intensive part that you want to distribute to various kind of hardwares coming in. And that's exactly where our forte hats in. And you can use any of these tools along with our tool as well. So we internally use Dask cluster as default to distribute our stuff, but you can swap it to Rapids or Ray or anything that you want on your end, and you can use it within our code tool as well to do it in. So let me just pause here and see if you have any questions coming in. No, perfect. Go there. Yeah, so just to give you an example, the classical, okay, so you see classical resources over here because we also support quantum computing, and there was a part for quantum resources. But ignoring that, the classical resources we support right now are Slurm, if you're familiar with high performance clusters that exist in national labs, AWS, all kind of AWS services like Fargate, Batch, Lambda, EC2, EKS, you name it. Azure, we do every service as well, GCP. Bad Kubernetes, you can spin up a Kubernetes cluster and ship it over there as well. Dask, IBM systems, you name it. We have plugin system for all of these things, and you can just install it and start shipping your code wherever you want. And as far as the software packages go, we are pretty agnostic to the software package you use in, because we package your entire function together. So as long as it's pickable, and we have written a lot of custom serialization on top of it, which means everything that we have tested right now, our serialization is able to do, except for pretty niche things. So we are pretty agnostic to any kind of package you use inside the code. And currently, even though the workflow or the task you write in is restricted to be in Python, in the sense that you need to write in Python functions. Inside those Python functions, we have given abstractions to write in C, C++, bash code if you want to run a bash command over there, for if you're running parallel MPI, OpenMP, or those kind of setup. And we are planning to add in support for Julia as well as time goes by. But for now, Python, C, C++, and bash tasks are allowed inside each independent tasks coming in.
Yeah.
All right, go ahead.
Okay. I guess I'll give a sort of the high-level review of the UX of just using Covalent. There's two main things you want to concentrate on. So here's a little mock-up of like a workflow graph on the right. The terminology here is going to be each task we call an electron, and the entire graph we refer to as a lattice. That's the two terms you need to remember. And corresponding to that, so if I have my Python code, I have a task here called task. In order to make that a task in my workflow, I just add this decorator on top. And then I can use that task in another main function or something like that. And I put lattice on top of that to indicate that this is going to be the workflow function. Then the third major piece is just dispatching the workflow. So one cool thing about Covalent is that if you don't want to actually run this on whatever remote compute, it's totally non-destructive when you add these decorators. So if you just call the function normally, it'll run normally. Nothing's been broken. However, if you want to actually send it off to whatever resources you've specified, in that case, you just wrap it in ct.dispatch, pass the inputs, and there you go.
Yeah, and one thing to add is this is one of the problems that you face in high compute environment compared to low compute model training or something is that typically when you run in a code model training or something, it might take in a couple of hours or even days in certain cases. So this asynchronous call of sending it to a cloud system, getting an ID back, and then re-querying it whenever you need is a pretty critical part to have. And so for instance, ARA works in a lot of research problems which takes in a couple of days to compute on a bunch of GPU machines. And it's almost impossible to keep a notebook live for couple of days, or even if you're sending in a script, it's pretty hard to maintain that script and reiterate it over. So these are the things that makes working with a high compute environment different than working with a low compute environment, which is what the need is turning towards, especially in the AI ML case, when you want to train stuff.
Okay, and we'll take a much more in-depth look at this stuff.
Yeah, we'll be running into tutorials, working with LLMs, some kind of general machine learning stuff and getting started as well. But just wondering, how many of you want to follow in together for the tutorials? There's a GitHub link over there as well that you can work with the tutorials with all the notebooks and everything on that side. But if you can just raise your hands if you want to follow up, we can wait along with it, or we can just show you the tutorials running it. Okay, sweet, I guess we can just go in.
Sure, okay. All right, so the first thing I'll show you guys is the bare minimum Covalent workflow. So this is also in our docs on our website. Actually, if you go to just covalent.xyz, you can find everything from there. There's our Slack, our GitHub. And what I'll be showing you is just a quick start from our docs. Yeah, thank you. Is the font a reasonable size, everyone? Is that okay? You can zoom in a little bit more. A bit more? Is that better? Okay. So if you do want to, go along with this, you can just scan this QR code here, or even this one. This one will take you to the repo. This is the specific notebook. Just clone the repository, the environments, and everything is set up in there. If you don't want to do it right now, you can even run it later. There should be instructions for everything. Okay, and the other thing to do is to just make sure we have Covalent running. In my case, I'll just type in Covalent status. Good to go, okay. Let me zoom out temporarily just to see the entire cell here. So like I was saying just a little while ago, we have electrons, we have the lattice, and we have dispatching and getting the result back. Here's a really tiny, actually trivial workflow. The only tasks in here are adding, multiplying, and dividing. There's nothing interesting really happening. I'm just going to add these numbers here, multiply them in the next one, and divide them in the other. You can see that each of those functions is labeled as an electron, so this is going to be considered a task in my workflow. And down here, I have my workflow function. It doesn't need to be called workflow, by the way. You can obviously call it anything you want. This is labeled as the lattice. So this is what I'm going to run through Covalent in this case. Let's take a look at what it's doing real quick. This number is going to be the addition of x and y. R2 is going to be just a list full of multiplications, and R3 is going to be a list full of divisions. The interesting part about all that is that Covalent will actually figure out how all these different tasks are interrelated in terms of the dependencies of the inputs of one to the outputs of the other. So you can see it's completed. We have our little result object that I'm printing here. R3 will be attached to this object. But you can see everything's done, some of the outputs on the nodes. And if I go over to my UI,
which you can find by the Covalent, by default, when you run it locally, it opens up a server over here in the local host. And that should give you a pretty neat UI for your entire workflow that lets you monitor the different tasks and different jobs that you are sending it out to the cloud or local on your side. So, yeah.
And sort of the centerpiece of the UI when you look at a particular workflow is this directed acyclic graph that it generates. In this case, it's quite simple, right? So there is one node on which the next layer of 4 nodes depend, and then each of those depend on another. None of this was explicitly specified in our lattice function, but the way things are set up, Covalent actually understands the dependencies here. So in this example, there's really no way to cheat at the very top. You have to run this one function. But once we get to the second layer of this graph, it's already been understood that these tasks are completely independent. So the parallelization there will happen automatically just right out of the box. In this case, it's happening in a Dask cluster that Covalent starts on my laptop. But if any one of these tasks was sent to a different resource, it would work exactly the same way.
Yeah. So just to add to it, I guess we just wrote a blog post pretty interestingly on running a federated learning model, which spins up each of these tasks runs on AWS, GCP, and Azure together, and combines the model together in a local instance. So in that scenario, your local laptop will be the central for your federated learning, and each individual task will spin up new machines, calculate it, combine to the local one, spin it down, and then go to the next iteration and start it. And so all these parallelizations are extremely useful when it comes to multi-cloud setup or even individual cloud running on multiple GPUs on your side as well.
Yeah, and another cool thing about the UI is that it sort of just keeps everything here in a record, unless you clear it, obviously. But so I don't have to reopen my Jupyter Notebook. I don't have to reopen VS Code, set up my environment again, or do anything really, because I can just come in here, click on a specific task. I can copy the output right there. What this does is it actually copies a little snippet of code that will load this into whatever.
The entire Python object.
Yeah, you just paste this into a Python script or like a Jupyter Notebook and assign the whatever comes out of the clipboard here, and then you'll just get the object there. In this case, it's just an integer that says 6, but potentially it's something more interesting, which actually we'll show you in a bit. There's also that you can do the same with the inputs as well, and with the inputs to the entire lattice function, so the workflow function previously. It's all there for you. Yeah, and there's a couple other things that you can play around with. Like
yeah, and pretty cool feature that I don't think we speak about over here is once you have this workflow, you can essentially redispatch this workflow with new inputs without requiring any of the additional dependencies or installations that's needed from any machine. So if you have a high computing job that you already shipped it to a bunch of GPU resources, and you want to spin off this entire workflow right from a Lambda function or a cloud function that you want to spin it, but just with new inputs. You don't need your entire package of PyTorch or anything installed in that Lambda function. You can just pass on the new input and say with the dispatch ID, hey, redispatch this again with the new IDs, and you can get back the result. So you can have it as a very scalable backend with submitting new inputs to a huge set of server, and the server will take care of spinning up all the resource and installing everything that you needed on the back end.
Mm-hmm. And if you have a question,
could you please show the example how it will work if we will have divide by 0? So
you error out?
Yeah.
Yeah.
Sure.
So he probably has already an error on his side. Yep. So you see the task has failed in on its side, and if you go to the UI, that just failed with them.
Yeah, they were identical. So I ran this node 4 times. You can see here. I'm running the divide function 4 times inside this list, and it depends on the outputs from the previous list. But since they're all dividing by 0, they all fail. You get your little error right here.
And you can do pretty interesting things. This actually reminds me, like, we do support the concept of dynamic graphs. So what that means is your graph can be built based on the result of the previous one. So if, for instance, you say this one errored out and you want to do something else, grow your graph in some other way based on this errored out, you can do that as well. And we have seen people use it for pretty interesting things like on-the-fly choice of resource that they want to have in. So they make query on which GPUs are the cheap in the cloud, and then ship it to that kind of GPUs on the fly after 2 days or 3 days if the tasks are running in on that side. So we do support dynamic graphs as they expand in the side.
Okay.
And do you have any support for developing electrons? So how do you develop the function, the electron? Because I don't know, do you have some workflow for developing the function that will be run as electron?
Oh, that's up. I mean, is this, maybe I'm not answering. This is the way you write in an electron on your side? Like the,
Okay.
Is your question like, is there a workflow to,
So the workflow, I don't know.
can you ship in as write packages on top? Is that what you mean?
Because it is very hard to write the good code that will be run on some, I don't know, big machine. And how do you write this small chunk of code that will be running on?
Well, ideally, you just write a function and pretend it's going to work. And usually it does. So the things you want to worry about is setting up the environment correctly. I'll show that in maybe the second notebook.
Maybe a more full-fledged LLM example would work in, but we do have, so for instance, if your question is, we do have people who have written packages on top of Covalent to, so for instance, there was a person from Berkeley writing in quantum chemistry codes on top of it, which requires a lot of compute on its end. And from his package, you can just import calculate energy of molecule. And that will be an electron in itself that he has written in a very clean way that you can just use it inside of your code. And in theory, you could have train LLM as an electron that you have written out and stored in a package itself that you can start using it to form workflows. So the ideal setup is that people write packages on top of Covalent to either expose electrons, which are just tasks in your thing that you then construct your workflow in or a pipeline in, or people have written pipelines in itself on top of Covalent where an entire thing is a pipeline in itself. So you have this entire graph in itself being shipped out as a code.
And can I use the electron function in unit test?
Yes, yeah. So this, outside of Covalent context, it behaves as a normal Python function in any way. That's one of the main thing, in fact, which I missed is, one of the key things we wanted to have is to write unit tests on top of these things. So every electron and lattice that you see here is a normal Python function outside of Covalent context. So it behaves as a, you can just call in.
So, if I pull that out and I have
workflow of
sorry, so hard to type
1,2. Okay. Oh, you have division by zero.
Right.
Okay, yeah. But it just behaves as a normal
runs the function, right?
Python function.
So there you go.
So nothing should change until you ship it to a Covalent server, and that server can be hosted in your laptop or cloud machine or wherever it is on your side. Here it's running in this local laptop. Until you ship it there, it behaves as a normal Python function on your end.
Okay.
Yeah. And as far as like special considerations, it probably depends where you're sending the function, but usually there's not much to think about. If you're referencing a local file and this task is going to run in a cluster somewhere, then obviously the file is not going to exist. So stuff like that you have to keep in mind.
Yeah.
But part of the design is that it's all you do is just specify the electron, and then the function is whatever. The function's up to you.
And just to add on to this as well, we have abstractions for you to transfer file from your local machine to wherever machine you are sending it in as well. So if you have your training data in your local machine or in an S3 bucket or whatever it is, we have abstractions. Probably can show it in over here. Let me see. So, oops, it's the other way around. So you can just add in to say that, hey, I need to transfer a remote file from my source path to destination using rsync, or I want to transfer it from using S3 bucket from, I don't know, Blob over here, Microsoft Blob with a strategy of, with my client ID and secret. And this transfers your file before your electron runs in the main machine. And once it's completed, transfers it back wherever you want it to as well. So there are different abstractions for you to make it easy to work on a remote machine right from your laptop. And that's the theme throughout this, OS code base. It has all the abstractions you need to run your Python functions in any kind of compute backend on your side with a single decorator on its side.
Another question?
Oh, yeah.
Yeah, so when you specify local, is that using like just synchronous execution, threads, multi-processes?
That's a great question. So by default, we use Dask cluster, spin up a Dask cluster wherever this is running in. But if you don't want to use a Dask cluster, we support multiprocessing as well. The problem with multiprocessing is that it doesn't handle memory really good on its side. So that's why we spin up a Dask cluster by default. And one of the example you will see is that we will, right now in the tutorial, spin up a Dask cluster on the remote and use that as a backend for our Covalent. But by default, it spins up a Dask cluster on its local environment that you're on.
So just as like an example, I haven't used Dask very much, but for illustration, if you have a directory of images and you want to resize every image together, one of the things you can do is just like open it in OpenCV, resize it, and then save it. Is that the kind of thing that you can do in parallel?
Yeah, that's one. So, in fact, I think, what was the ML example in Dask that you're running in?
It's not resizing. I think I have an LLM describing.
Yeah, describing. So what he does is instead of resizing, he has a folder of images which we'll run in the tutorial and read through the image and use LLM to describe it. But that's pretty much the same. Yeah. Yeah, that's what people use it in for as well.
Yeah, actually, there's a cool feature in the second notebook that's sort of relevant to that.
Oh, yes. We do have the concept of triggers as well to trigger your workflow based out of any event that happens.
Just sneak peek at that real quick.
Yeah, there are really a lot of nice features that I don't think we are going in on this one, but okay, here's an example. So I guess you're attaching a trigger to your lattice over here to say that, hey, trigger this workflow whenever, this is a directory trigger, whenever an created event, which is like creating a new file and this trigger happens, and ship new batch size of 2 recursively to all the setup. And we have SQL-based triggers, so if you have a new entry in SQL, you can trigger a workflow of that. What else do we have? We have time-based trigger, so you can trigger your workflow every 10 seconds or in a cron or what, yeah.
Does it do caching for that as well?
Oh, yeah. Everything is, so by default, everything is completely cached in Covalent. You can turn it off, but every data, input, output, file, everything is cached by default. And that, where it caches, it typically caches in a local folder, but that could be an S3 bucket or any kind of storage that you want to have it in that you can configure.
Does that mean you have to use hashable inputs?
No, because we serialize everything on our side. It doesn't need to be, any Python object, we don't care about it. So it could be an image object, PIL image, on your case, whatever it is. That was one thing we are very strict on, is that user doesn't need to think about the fact that you're running it in Covalent. You just write any normal function and you add it on top and it works automatically. Except for there are very few niche things that is not pickable with our serialization. One example is typical Boto clients or GCP clients are not pickable because of the security credentials on its side. But you can work around it by instantiating inside the function, and that will work in as well. So we haven't seen any major problem with pickling or using this setup in our side yet on our end. Yeah.
Okay, so let's not jump too far ahead.
Oh, yeah.
Come back here. Let me just rerun this one more time, just for fun. So I guess another point here is that if you have this dispatch ID handy, you can do this get result call at any time, right? So this is completely independent from doing the dispatch. As long as it's cached, as long as you haven't purged all your Covalent files or anything, it doesn't matter where the workflow ran, the results are brought back and saved for you. So as long as you have Covalent running, as I do, it doesn't even have to be running locally. You can just do a get result request to Covalent and pass it a dispatch ID, get everything back, and you have this result object with a bunch of information, as well as the actual return value of the function there. I just reran it, but that's okay. Yeah. So I guess that's all as far as the intro. Of course, if you go in and rearrange this function, the graph will look different and all that.
Yeah, and one thing to add is this is a very scalable graph in the sense that we have tested close to 10K nodes or 50K nodes on our end, and everything remains fault tolerant and completely stable on our side. So it's not just meant for piping in small chains of data flows on its side, but really huge graph that you can handle in on this setup.
Okay, and on that note, I think we can move on to a more substantive tutorial. Okay, so this one, we're going to use Covalent with a remote Dask cluster instead of having it spin one up on our own machine. And to set up the Dask cluster, I've included in the tutorial, actually. If you navigate to the repo, this is number 2. So you can see here reference to a README file over here. There's a README in there. The Terraform isn't really the point of this. I'm just going to run a little setup to make the infrastructure in AWS, and we'll see how to work with it, OK? So I will just do that real quick here.
Oh, can you zoom it? Great.
Is that better? Probably go more.
Yep.
Where am I? If you guys has anyone worked with Terraform before here?
Oh, yeah. Yep. Oh, OK.
So it's how would you describe? I guess an infrastructure as code tool.
Yeah.
So what I'm doing here is just making a couple EC2 instances on AWS. I'm going to have one be the Dask scheduler and the other ones be the Dask workers. There's nothing fancy. It's going to be all static. It's just going to sit there, and I'm going to have just an address that I can plug into Covalent. So to do that, you need a little Terraform init. I'm going to copy the code from the README, actually. Find it out. OK, and if I have my credentials set up for AWS, that should just take a couple minutes there and do its thing.
So this here, we are creating a remote Dask cluster to run it in. And one of the feature requests that we have been asked a lot of time is typical end users for the Covalent or data scientists, research engineers and other folks coming in. So they're not familiar with Terraform or not that adept at Terraform or spinning up cloud resources and other setup. So what we have in the next set of releases in the open source is that you can essentially do Covalent deploy AWS batch. And if you have your credentials right, it will automatically spin up an entire batch cluster on your side without you even doing anything on AWS. And you can start using it right for your workflows in your setup. So all this, even working with Terraform to spin up your infrastructure, will be abstracted out to make it easier for you. And what that means is you don't need to even touch anything in Terraform or cloud. You can directly start using it right from your terminal on your side. So that will be pretty neat to have it. And so we have it on AWS batch, GCP batch, and Azure batch coming in a couple of months from our side.
Yeah, and also what you're seeing now is I screwed up and had a typo in the docs, which I will update. So that quote should be all the way here. So just give me a second to undo that.
Yeah, any questions while this is running in? Oh, yeah.
Yes, could you go a little bit more in depth? If, like, for example, I must learn an executor and I have dependencies in a certain task, like how, like,
Yeah, perfect. Yeah, sure. Can you go to the docs? Yeah. So, I don't know why this is. Okay. Okay. So the way you kind of define dependencies in your cluster is we allow for multiple, essentially dips, dependencies on your side. You can have dips pip, dips conda, dips bash, which means you need to run a bash script before running your task in. And you also provide hooks for defining custom Python function to run before your function or after your function. So let's say you have certain dependencies on your side to run a NumPy. So you need to install NumPy in this remote machine running in. So what you need to do is add in a quags called dips pip, and you just say, hey, you can either pass in an entire requirements.txt file for that, or you can just say my packages or NumPy is what I need to install on that side. And what this will do is this will essentially, before running your function, install everything over here, run your function, and then tear it down. Or you can even provide, for some weird reason, let's say you want to install it after you run your function, or you want to do very custom thing after you run your function. Maybe you want to delete credentials in it or ship that, take the files and put it somewhere else. So we do provide call before and call after hooks for you to pass on any Python function over here or even any dependencies over here to be executed before or after your function runs.
Actually, I'm pretty sure you can just pass the string as well.
You can just pass your string in. So here you can just pass a list of dependencies over here as well. Just like I guess that's how Hara would have done it on her side. Yeah. So that installs, is it here?
Yeah, so I'm
yeah,
just
here
doing
it
a
is.
list of
Yeah.
Just literally.
So this one needs below torch fission, transformers, and you just pass it as dips over here. That's it. And this will install it right before your function runs in the VM. And yep, go ahead.
Can you also specify which Python path to use?
Oh yeah, you can. So we do provide bash deps as well. So you can edit anything that you want. Yeah, bash dependencies, here it is. So you can send in any kind of commands that you want to set in before your setup. So if you want to change your source, change your Python file, change your variable, you can just do it there as well. One thing I haven't mentioned is this. What this means is this is typically useful. This dips pep is typically useful if you're iterating as a researcher, trying in various packages and other things. But once you are done and you want to send it to production, it's typically not useful to install everything before your task runs in. That's not ideal. So what you can do is for our cloud-based plugins, executors, you can attach any custom images you have on your side as well. So if you have an image, a container that's preloaded with all the packages already installed in it, you can pass the image in. That way you shouldn't, that's typically for production on your side if you want to convert it. Yeah.
Oh man, I really.
Oh, it's taking its sweet time.
Yeah, it's taking its.
Oh, pretty surprising. It's just he tried it yesterday and it took him like 28 seconds to spin up these new things.
Yeah, because I botched it and I destroyed it right away. So now it's getting all confused. But this is Terraform, not Covalent. Okay, just everyone blame Terraform for this. I might actually just.
Oh, sweet.
Great. Okay. So yeah, that quote should be there. Okay. Too many. Really? What did I screw up?
Double var, maybe. No.
Maybe just do the apply for us.
Var. You can do var twice.
Yeah.
I don't know why it doesn't like that. Huh. Expected at most one propositional argument.
Never go with live demo.
Oh, I'm sorry. Okay, hang on. Sorry. This should be the plan, and then, yeah, okay. Man, I must have been really sleepy when I made that README. Out, task.tf plan. In Terraform's defense, if I was be doing this manually, this would take like 30 minutes. So it's a lot. There we go.
Okay.
Sweet. So now we actually wait for it. Sorry, guys. Does anybody have any other questions, maybe?
Yeah, while this is running in, I guess, for the curious few, I can show in the kind of plugins we have in. So we do have Dask. We have SSH that lets you connect through on-prem GPU systems or any SSH machine you typically run your code in. And for that, just to kind of see the UX, it's like, you can set defaults in the configuration so that you don't need to pass on anything, and you can just say, hey, run it in SSH, and it will use the defaults that you are passing it in. But if you actually want to pass on object, you can say that this is my username, host name, here's my remote directory I want to store my results or whatever assets that develop in, and then here's my SSH key, and then just tap it along, and that should be the SSH. Slurm, again for HPC or HPC users. We have a list of AWS plugin, EC2. EC2 is pretty interesting. It will spin up a new EC2 instance on its own, run your code, shut it down. You don't need to do anything. And this interaction is as simple as, just say, hey, I need an EC2 of instance this type with this volume, and here's my SSH key. It will take care of spinning up everything on the background. You don't even need to work with Terraform. Lambda is pretty neat as well. If you want to run Lambda functions, you just say, here's my Lambda function name, here's my S3 bucket to store all the inputs and outputs, pass it on, and it will spin up a Lambda function for you. So Cloud, Executor, Azure. Ignore these things. These are quantum computing executors. It's IBM's quantum plugin, Qiskit. Amazon has its bracket service for quantum. Ignore these things. And we do have contributor plugin that lets in any kind of HPC system that they have in. People in NERSC, which is the Berkeley lab, they use Covalent as well, and they have made their own plugin to interact with their cluster on its side. And we do let you create your own custom plugins as well. You just copy this template, And to give you an example of how easy it is to create your own plugin, let's look at one of the contributor plugin. And it's at the most, I would say, 500 to 400 lines of code for you. So the reason people would do it is if you have a very unique system on your hand that you need to connect to, maybe your SSH system needs multi-factor authentication because you are working in a private setup. So this lets you write your own plugin in how much ever you want. And you just need to override a couple of functions to write your own plugin. Yes?
I was going to ask how the file abstraction works. If you can accept like S3 buckets or Dynamo databases or something.
Yeah.
The key and deletion management looks very different from local resources. What is?
Yes, we don't do Dynamo yet, but we do have S3, and I can show you an S3 example over here. Oops, here's the. Okay, so let's see S3. Okay, so here it is. This is the UX you have. And so you define a strategy, and typically the parameters you pass in for your credentials go into the strategy. So let me see if there is an example of credentials being passed to S3. Okay, we don't have the credentials being passed on. But typically this contains all the credentials and everything that goes to the S3 transfer. And then you say, hey, I need to transfer my file from my source path to final path using this strategy. And you can even pass the order to say that, do I need to do it before the task or after the task has been completed on its end? And you just tag along to say that, hey, these are the file transfers I need it to happen. So I have 2 transfers, one by default, I guess, before the task, and one I say after the task. So before the task, I pull in something from the S3, do some computation over there, and transfer it back to S3 after it's done. And just to kind of, and that will be the same for remote blob storage. Here is an example of blob with. So just like how you, in the S3, you would have something like this to pass your credentials or keys or whatever you want to pass it on. And pretty much the same syntax over here. And this, again, all of this are modular, and we provide abstraction. So if you have very custom DynamoDB, you want to extend it to DynamoDB, you just subclass the strategies and write your own custom setup however you want it to on your side. Yeah. Let's see if it's, it's done.
What are we doing there? Okay. Okay, so it's outputted a scheduler address for me. This is just the public IP of the EC2 instance. That's going to be the DAS scheduler and a port number. I'm just going to copy that. Let's go into the notebook.
Okay. So by default, we use Dask as well locally. So Ara will now show how to use a custom executor object to change your attributes.
Okay. I'll actually just go through this cell by cell, just so we.
And what is the thing we are doing in this experiment?
What is the?
Yeah.
We're gonna. So here's a little preview. I have these 2 folders. This is my triggered folder. This is the one I've set up to be the triggered folder. And when I drag and drop images in here, so maybe this is part of like, I don't know, you have some
pipeline.
You have some pipeline, yeah. There's images coming in that need analysis. You have an ML model that can do that, and you want that to happen automatically, but only when there's new images. You don't want to waste time rerunning that over and over. So what I'm going to set up here is a really simple version of that. Anytime someone drags in 2 images, which is also a parameter. So if I put in 2 images into this new folder, it will trigger a workflow. It will analyze them, and it's going to write a short 1-line description in this, at the moment, empty file. That's what we're going to see here.
And the reason that you would typically want to use Covalent for this example is, so for instance, one of our customer using the open source has a huge petabyte of video file on his side, and every time an experimentalist uploads a petabyte of this video file, there is a pipeline of machine learning process that needs to transform this every time happening in. And typically that conversion requires 5 or 6 GPUs to run together on a site. So you can't have 5 or 6 GPUs running on the cloud every time to just tap along. So this takes care of spinning up a new instance. In this case, we are using a Dask cluster, which is already running, but this could be swapped for any kind of executor on its end. And it'll spin up a GPU just for this file, run it in, close it, and call it a day. So he has a huge saving in cost by just spinning up GPU whenever it's needed on his end.
Okay, and I'll just walk through the notebook here. Nothing special going on here. This is going to be what the descriptions look like. One thing to note here is that you can also use like other code with Covalent. You don't need to decorate everything with lattices or electrons. So I have a bunch of utility functions. I'm just going to use them normally. And whatever task they get wrapped up in that I actually want to send, that's the one I mark. It's going to take care of all this. It'll be wrapped up and sent in and ran remotely just fine. This is going to load the model from Hugging Face. I'm using a pre-trained model to do things quickly here. Here's just some filter functions and a class for the image and its description, so I can manipulate it and show it to you guys at the end of the notebook. OK, so here's the first electron. This is the first task in my workflow. It's a lightweight task. I'm going to run it in a local process pool. And so I've specified local here. What is this doing is it's looking through that directory. That's just the constant at the very top. It's going to look through that directory, and it's going to filter only images, and it's going to filter only new images, and just return the list of that. Here is the task that uses my remote Dask cluster.
And just to add to it, to answer your question, there is no special JSONable input or output that we need to have, and it's Python objects on our end.
Yeah, so here at the very top, I'm making a custom instance of the Dask executor. This is also the default executor, but here I'm customizing it with a scheduler address. And what that is the number I pasted in at the top of the notebook. And then it has some pip dependencies like we talked about. That's just going to be a list of these strings, exact versions, all set. And here's how I apply it to my function, c2.electron, specify the executor, specify the dependencies, and that's all. So what's happening inside here? I'm downloading an input processor. I'm downloading the actual model. These are just stuff from Hugging Face. You can go look into these models if you want. And then it will use CUDA. The reason I've put it in a conditional is so I can test this locally as well without breaking things. Yeah, so it's going to run through each of the input images. It's going to pass them to the model. And it's going to generate a sentence to describe the image. So it's going to be a little bit silly because it's a tiny model, but it does work, as we'll see in a second. Run that cell. Last thing I have is, so this is another local task. It's just going to write the description into that file, OK? So I come down to my lattice. Yeah, what am I doing here? I'm just using those three functions. Yes, and the trigger, like we talked about. So you pass a list of triggers to your lattice. The particular one here is a directory trigger. It's triggered every 2 items that are created. And I'm not going through the directory recursively. It's going to be a flat directory. It doesn't really matter. You can actually get rid of that probably. OK, so I'll run this.
Once this done in the UI, you should probably.
No, so it's triggered, right? So it won't do anything until I drag and drop. So let's see, which one do we want to see here? We got birds feeding, birds flying, lemurs, monkeys. Let's do the monkey with the pipe, and we'll do the birds. So if I pull that in, live demo, please don't betray me. Come over here to Covalent. Oh, it didn't like that. OK.
Oh, there's a huge error.
That is not good.
Maybe your Dask cluster is down, probably.
I think so.
No.
Well, I'm just going to try it again. So if something goes wrong, you can do a Covalent restart.
No purge it in as well. No.
Sure. You can restart extra hard if you want to purge. So the resources will stay up. And I'll just make sure that's specified correctly at the top. OK. Oops. We're back. This is really cool. I hope it works. OK. Let's do these guys as well. Okay. So I'll put that in. Cross my fingers. Refresh.
OK, it's running in.
There we go. So this has been shipped off to AWS to that schedule address. It'll take a few seconds to actually do the generation. And once it gets back to us, we should see a little description appear in this catalog file, which is still empty at the moment.
Yeah, but then, so if you have a pretty large workflow running in that spins up multiple GPUs, yep.
Just thinking through use cases as well, can you make workflows that subscribe to like Kafka topics, for instance?
Yep. Yeah, exactly. And we haven't done the subscription, but that event trigger could be anything. So we have exposed abstractions to write any kind of triggers you want to have. So oh, is it done? No. Okay, while it's going on, I think, just to kind of, even I forgot what are the triggers we have in. Most of the triggers were actually written by external contributors as they see in new features coming in. So let's see the triggers. So I think we do have directory, time-based, general database-based, Postgres, I guess, and SQL trigger on our side. But that could easily be external to any kind of trigger that you want to have. And I guess so for database, be something like pass on the Postgres to say the DB path, the table name, and then you pass it on as this over here, and you give the poll interval, how many triggers you want to do, and it triggers it.
Yeah, and all this is open source so far, by the way, as well, obviously.
Ooh, it's taking a sweet time.
That's unfortunate. This worked for me. This is me being bad at Terraform.
Okay, but one thing we can do is just swap the cloud to local.
Sure, okay.
And that should probably just work in. We have those things installed locally.
It should be in this environment, yeah.
Yes, local. And now if you just put on these two, let's see. And this keeps turning over.
Yeah, what are we bumping into, I wonder?
Okay, and you just saw how easy it is to swap the same thing to run it locally on its side, and now this is running locally. And I guess this might take in time locally because it needs to download the model from Hugging Face on the side.
It was nice and quick for me this morning, I'm not sure. Was it still in Dask? Did you sure you swapped it?
Yeah.
Okay.
But I guess we could probably just move on to the...
I can move on to the next one, yeah.
and come back to this once it's done.
Unfortunately, that was my favorite one. Okay.
Okay, so the next one is a bit more realistic example of shipping it to not just a Dask cluster, but here I guess we're using AWS Batch on its side, which is much more important for compute-intensive tasks that can spin up GPUs or any kind of things on it. And so, working.
Yeah, so I also have Terraform to set this up. So I will do that as well here. This one's quite a bit simpler.
And this workflow is interesting workflow because it indeed uses multiple, it's important to use. Oh, one thing is done. I think your Dask is done.
Is it?
Yeah. Over here?
Yeah,
over there?
thank you.
No.
Yeah, that one.
Yeah.
Oh, sweet, okay.
The cloud one is done, so I think your...
It was just taking a minute, I guess. Okay.
Yeah, your notebook
Sweet.
should be updated.
Let's see what it
Oh, sweet, okay.
Can you guys see that? It's not done a very good job. You could probably just use a bigger model to get a nicer output, but...
Group of ringtail. Okay, it does trigger its...
Group of ringtail lemurus. Close enough. A bird feeding its young birds in the nest, I think. That's pretty good. Oops. That's the bird
feeding.
Yeah. There's the lemur one. It's done pretty good at that. 2 monkeys in a tree. I believe it was 3 monkeys, actually. Monkeys howling. Yeah, missed the 3rd monkey. And a chimpan smoking a pipe. Well, it's actually a chimpanzee, but good enough for a model that you can get in about a minute. Okay. Sweet. So yeah, apologies for the delay there. Anyways, let me spin up the resources for the AWS demo here. I've also included a README for that. The instructions here are much simpler and don't contain typos, unlike the other one.
I somehow think this is the one that's going to error out pretty badly.
You think so? It is more, the actual workflow is much more complicated. So there's a lot more that can go wrong here.
Yeah, so this demo, the one that we're going to do now, is actually uses a string of tasks to do it in. So can you explain what the workflow is over here?
Sure. I probably have a version of it that I've already ran. I think maybe this one.
Yeah. So this is a pretty complicated graph that you see there, but I think you should probably zoom in because it's not clear over there.
Sure. Make it a little bit.
No, I think zoom in the graph, I guess. Yeah. Yep.
So, okay, we can see, actually, so before I zoom in, there's maybe 3-4 layers of stuff happening here, and a lot of it is going on in parallel. So I have a bunch of sections from a Wikipedia article, for example, MC Escher. That is not the Wikipedia article. Here we go. So this stuff, right? These sections. And my workflow is going to generate an image to describe each of the sections that I've specified. We'll see that in the code in a minute. But in the graph, so I'm going to batch those sections into a batch size of 2. And then I'm going to spin up separate instances to do each one. And, well, I'm not doing it. Covalent's going to do it for me. And you can see that happening in parallel here. So I think I have 6 sections in this particular article, 6 or 5. So we have 3, 2, 2, and 1. These branches will start up simultaneously, and then we'll work our way down. So this task will grab the text from the section. This will generate a summary using an LLM, and then we'll use that summary to prompt an image generation. Obviously, there's a lot of compression happening, so the images are going to be pretty funky. But just for the demo. And then everything will be combined into this post-processor object thing that I wrote, just a little class that's going to help me display it nicely in the notebook.
And what's critical here is that few of these things are pretty low compute tasks, so I don't need a cloud resource for it. So for instance, the get page section just uses a local Dask cluster, as you can see on the top, saying Dask in. And generate reduce summary uses a text-based LLM on its side, so it's not GPU intensive, just CPU intensive. So I've attached an AWS batch that spins up, I guess, how many cores? 10 cores? Or
I forget. It's in the executable.
yeah, some number of cores of just CPU alone, while the images is pretty GPU intensive. So that spins up a separate GPU instance on the AWS to run it in. And these are all spin up on-demand serverless. So what that means is we don't keep on running a GPU or CPU instance on its side. So whenever the task is needed, it spins up a new machine, calculates it, shuts it down, and goes to the next one. So you just use the time and cost of how much ever the computation you're doing and nothing else and nothing more. Yep.
All right.
So let's see if it's spin up in AWS batch.
All right.
Yep. Okay, so once you run the Terraform, you get all the parameters that you need to pass to your executor. And this will be abstracted from the next release. You can just do Covalent, deploy AWS batch, and it should do all of this automatically and give you back the final arguments that you need to pass in.
Mm-hmm. And eventually all of the other ones ran as well, just for the record. So save myself the, yeah, okay. In this case, these are actually already in there, but the only thing we need is a unique S3 bucket, and it's going to be a new one every time. So the only thing I'm going to copy in is just the name of that S3 bucket. Okay. So what am I doing here? I'm updating my default configuration for AWS. And there's a few things I need here, which are the outputs of my Terraform. In this case, I want to point it to my actual credentials file, like that. And the rest of the stuff is already there. So what this does is updates the defaults for the executor so that I don't have to have all these fields in every object that I instantiate. So I'll run
You
that.
probably need to restart the Covalent after setting the default as well.
I think it actually works like this.
Okay.
Yeah. If it doesn't, I'll come back. But yeah, so the tokenizer is going to be T5 small. Again, tiny models. The output will be a little bit funky, okay? Just forewarning. This class, nothing fancy. This is just my little hack to display the things in the Jupyter notebook. It's just going to print out the images. You'll see what this looks like at the very end. I don't have to do anything special here. I just use it in my code. OK, this one downloads the model. quick look at the workflow, at the electrons you saw. This particular task is going to use the Wikipedia API to read the text from the thing. It's going to run locally. Nothing super fancy there. Okay. Here's my first AWS executor. In addition to all those defaults I set up there, so I can just make one and say, in this case, I want 2 GPUs here. I want 12 GB memory and kill it after an hour if it's not done. And then I pass that to the lighter of my 2 heavy tasks, which is the text generation, along with the pip dependencies like we discussed. Below this, I have the heavier one, which is the generating the image from the condensed summary that comes out of the text model. For this one, I add in here that I want 1 extra GPU with it as well. And yeah, all the other default settings will apply. Pass that to my task with the dependencies here as well. The last task here just puts it into a post-processor object. Yeah, it's going to run locally, nothing too fancy here. The reason to include this in your workflow is just to be able to cache the output here. So I can go back actually to my previous workflows here, like the one that completed. And I should have that output here. So I could just grab this, paste it in, and see the results from this as if I had just ran it. So that's the reason I'm including this local electron in my workflow. Okay. The main function just uses all those functions to do what you saw. The logic that it follows here is reflected exactly in the shape of this graph here.
Just to can you go back to the lattice over here? So I don't know how many of you are familiar with Airflow or any of those sorts. Yeah. So typically, if you want to construct a complicated graph like this in Airflow, it involves a lot of DAGs that you need to define it over here. But here it's pretty much just a Python function to take care of dependencies. And as I said, the main goal for us was to build a very stable backend that can support thousands of nodes on its side. So the goal needs to be to create very easily thousands of nodes of graph that you can have and to control your system. So yeah, it's just an example of 3 different parallel tasks we are doing here, but in theory, this could be hundreds of parallel images that you're generating, and everything should be handled fault tolerantly, pretty safely on this side.
Yep. So yeah, what we can see this is the brand new workflow graph. It corresponds to the dispatch ID here, D2AC.
And I guess he has put in a wait equals true command here to wait for the results in. But if you don't want in, you can just dispatch it, close your Jupyter notebook, come back after a couple of hours, and then get this dispatch ID and re-query the result, and you should get a live result of whatever is running. So if your status is still running, it'll say it's still running and give you back the results of whatever is completed. You can do whatever you want, and you can cancel it. You can redispatch it. Let's say you don't want to use this model and you want to reuse a different model for your reduced summaries. So what you can do is grab this dispatch ID, redispatch it by just swapping this electron alone on your side. And what this will do is it will not compute anything that's already computed and just start from the point where it needs to start to. So that way you don't need to, if you're using a lot of GPU resource on the previous set of tasks, it doesn't need to recompute it, respin it up, it'll just start from wherever it is. So these are the critical things that's needed for high compute because these are pricey computations and you want to be pretty careful on what are the things that you recalculate and do on your end.
And what's cool about this is that you can just go back and if you want to modify like this is using a bunch of cloud infrastructure. It's communicating a bunch of information back and forth. If you want to change any of that logic, it's tied just to how you define this function. So you don't need to think about applying that on the AWS side at all. You just come back in here. You can take apart this loop. You can have less items in the loop, more items, different inputs. It doesn't matter. It will figure out the best way to run it, no matter how you write the function here as well. And if I wasn't waiting for the result here, right after you dispatch it, you can come back, change some stuff up, dispatch the other version as well. This executor is much more robust than the Dask example I showed you where I manually set up the resources. So in this case, the AWS Patch executor, it does everything for you. It goes through AWS Patch, it creates and destroys the instances as you need them. So much less to worry about. You can just send as many jobs as you like and then get the result whatever you want. I believe this particular workflow is about 15 minutes of runtime. If I look at the last time it worked. Yeah, 13 minutes. So maybe
You can just show in the.
I do have the results from last time, so you can just look at quickly what we get from it. Okay, what have I done? I've looked at MC Escher. We all know MC Escher, right? Crazy Stairs, right? Okay. So the sections are his early life, study journeys, later life, mathematically inspired work, and legacy. Here's a slightly disturbing image, I suppose. Apparently this image corresponds to this very short description of his early life, where he was born, his parents, and their occupations, schooling, etc. This is mostly just for fun. I like this one a bit more if you ignore the very creepy person in the corner there. What does this supposedly correspond to? It's that he went to Italy, visited Florence, San Gimignano, I don't know, Volterra, Siena, and Ravello. Impressed by the Italian countryside, et cetera, et cetera. I don't need to read all that. Moorish architecture is perhaps where all these arches came from in the image, but who knows? This one's a little bit interesting. It looks rather stamp-like, and the reason for that is because the thing that it decided to summarize from the particular article section is the fact that he designed some stamps in 1949. So that's a very powerful word there, and so it made the whole image look like a weird nightmare stamp from MC Escher. This is quite cool. I would have this in my house, I think. It's just about mathematical techniques in art. And finally, here's another one. This is about a retrospective exhibition that took place in a museum somewhere. And the reason you're seeing this sort of spherical distortion is because of this little bit down here. It's based on hand with reflecting sphere. There's this famous photo of Escher holding a shiny sphere in his hand, and you can see his own reflection in it. So the mention of that has given us this nice spherical motif here in the output.
Yeah, the pretty cool thing is, I guess, you can just show in this one, which is while this is running in. So this is a completed workflow, and I guess the end result is this. Of this is the final thing that Ara just showed right now. And what I do is I just click to copy this entire thing over here, the result, and I come back to my notebook. Oh, this is a running notebook. So I can just go to any other notebook that I have in over here and paste it, shift enter, and this should, let's see. Oh, it's pretty large.
It is, yeah, it's a bunch of images. You want to run the display all method on that object.
Oh, is it?
To get the pictures
What do we
out.
get in as result, do you know?
I think you do out 12. Does that work in a notebook? If you index it.
Which one, sorry?
Underscore also works.
Underscore is the previous return?
Oh.
Oh, cool, okay. So underscore dot display all.
Oh, sweet. Okay.
Yeah, it's actually the same ones I showed.
Oh,
So that's
it's the same one, okay.
that's the one from this board.
Okay, but the best part is that, if you're hosting this Covalent on some other EC2 machine, the server in itself, and if you're sharing the workflow between multiple guys, you can just copy the result and look at it in his local laptop, just like that, without needing any extra setup or downloading anything on his side. And that's true for, that's true for any of the midway results for you to cache in as well. So these are a couple of warnings that have evolved.
It's just the progress bar
Okay.
is the output from the task, so it brings that in.
But this is true for any kind of outputs as well. And this is done with the CPU task, and it's going on to the GPU task right now. The CPU task, I guess, took in how long? 4 minutes. So I guess this is the pretty neat thing. Whenever you're combining these things, you have all the metadata and everything that you cache over here. Oh, man, I'm not sure what I'm tripping on.
Is it the table? I think it works. Okay. Anyway.
But cool. So this is a good example of how to use the open source on our side. So I guess in the 10 minutes we'll just give a preview of the cloud version of this, which is a bit more interesting with a lot more abstraction on its end. But let me just pause here to see if anyone has any questions. And yep.
So what does memory management look like on your side? I noticed that you're using global variables in things that are on different executors. Do you just copy the execution environment to each different place that gives you access to those variables?
Oh, so we serialize it on our side, all the global variables are serialized on its end. So the function, the pickle size of this function depends on the global variables that you're using.
So does that mean instead of defining requirements, you can just import them at the beginning of your
Yep,
file? And
you can.
they're
You can.
assumed to be
You
requirements?
can, yeah, on your side. But it'll just make your bloated. Your call on what you want to do with it. Yeah.
Last question I had was on dependency propagation. So can you say that, so if you run one task locally and then the next one on cloud, and A depends on, or B depends on A, and A has a certain set of requirements, does that requirement set also apply to B, or would you have to independently specify that the two requirement lists?
That depends on what you're using. So if you're using, say, PyTorch in A, and you don't need PyTorch on B, you don't need to have it in. But if you need PyTorch in B, you need to specify this dependency as well.
You have to explicitly.
Yeah, but you can, if you think everything in your task uses the same thing, you can just pass it to the lattice to say that, hey, all of this require all of these things on your end. And it'll be propagated to all the stuff on your side. Yeah. Any other questions? No. Okay, I guess we can move on to
The cloud version.
Dude, I don't know what I'm doing over here.
Is it you? Might be this little cable here, okay? Just, yeah. Okay.
Cool. I guess so.
A couple of slides from this.
Just moving on, the last section is about our Covalent cloud. Obviously, it's developed by Agnostic on our end. So we have a cloud version of this compared to the open source version. It's pretty much the same as open source version that you see over there, but except you get in few more interesting things out of the box. So open source is meant for individuals. So you don't have the concept of multi-tenancy or multiple users using the same server to send in jobs or whatever you want. But the cloud does support for multiple users to send in all the jobs. But the more interesting thing is that you saw that over here, you still need to be aware of the fact that you are sending jobs to AWS or EC2 instance or batch or anything that you want to do it in. But what we provide in the cloud is completely abstracted cluster on the cloud for you. So all you need to say on your end is, hey, I need 32 cores of CPU and 5 GPUs of H100, and we provision it for you from any cloud that we find fit. And you can give in constraints as well to say that I need the cheapest compute, or I need the fastest queue time, like maybe H100s, I don't need to wait a long time, I don't care how much I'm going to spend, just give it to me. And we pick the right kind of cloud provider you want to have it, and we ship it over there. So what you, as you say here, it's pretty much the same as open source, except we have a new executor called the Cloud Executor, which will show up pretty soon there, yeah. And over here, the key difference is that instead of adding in dependencies every time, we provide abstractions for you to create environments as well. So what you can do is you can create an environment which essentially abstracts a Docker image on your side. So you say that, as Ara put it out over here, you can say that, hey, these are the pip installs I need, these are the conda installs I need, and pretty soon you'll have custom images that you can pass on as well. And this will create a complete Docker image and store it on the cloud. And you say, hey, my tasks needs to use this environment. It requires 2 CPU, 12 gigs of memory, and even GPU of type T4 or whatever it is. And you don't need to worry about which cloud it sends into, which place you ship it in. And it's our responsibility to have our own cluster to ship it in. And pretty much rest of it remains the same on its end. Go ahead, Radha.
Yeah, so this is the same notebook. 13.
Yeah, it's essentially the same notebook, except
really, all I've done is to swap out the executors here. So I have, let me come back up to the top. So the cloud executors, like Santosh said, are fully generic. All you care about is the environment and the resources. There's no like credentials to supply. There's no log groups and batch queues and stuff to specify. You just, the only thing you specify is what you want and what you're interested in, which is certain number of processors, memory, and the particular environment. The environment you also make yourself. Here I'm referencing just the pip requirements file that I have somewhere here. The Python version, etc., conda, pip packages. You can do a bit more stuff in here beyond just these two, but alas. So as far as the actual workflow code, what I'm going to do is specify the new executors for my tasks. In this case, I'm going to run everything on the remote cloud, so I don't really have local tasks anymore. I have lightweight CPU and GPU tasks here, so all the lightweight stuff I put on the CPU executor. And it's really just the same code. Again, use the GPU one here. You can see that I don't have anything like deps pip over here. because I don't need to, right? So all the environment stuff is baked into the executor, which is referencing this environment that I have in my cloud account that I've set up like so. Okay. And I definitely don't have time to run all this, but the last thing to point out here is that this is a lot more scalable than the OS version. So what I can do is I can dispatch 9 different versions of this workflow just in one shot, and I'm not worried about it weighing down my PC or anything like that. And that's exactly what I do down here. So in this case, it's cc.dispatch, CCP.
So I'm dispatching it to the cloud server. So
Yeah.
this is one of the main setup that people have been using in actual startups. Have been using it on the LLM side. Is you don't want to work on the compute part of it. So your forte is not actually infrastructure or creating compute. So you offload it to us. And you say from a Lambda function, hey, I need to rerun my function with new set of inputs. And everything on the background is taken care by us, from spinning up GPUs, running your code and everything. And you just get back asynchronous IDs that you can query back the result whenever you want on your end.
Maybe it's me, huh?
Yeah.
Sorry. Yeah, and then you ask for them back, and
We can show in the UI as well.
come back over to,
All right. So I guess the cloud has a bit more, fancier UI on that side. So RS ran in a bunch of experiments on its end, and I guess which one is the one that you had it in? And this is how you see all the
Yep.
workflows that you put in.
So here's all the 9 things I've dispatched. I've come in here and added a tag to them just to know what's what. They all look about the same depending on how many sections. In this case, there was only 2 sections. Or perhaps only 4, since the batch size is 2, and so we see a different number of branches.
Yeah, and you probably will see the resource it's used in. So this one uses divided by 1048 on its side, 2 CPUs on its end, and doesn't use any GPU. And the generate image uses 4 CPUs on its end and 1 GPU of type T4 on its end. And the environments that you have created resides over here as well. So you can see that Radha has a bunch of environments which contains different packages. So you can say that, hey, this task only depends on SciPy and whatever it is, and the other task depends on a multiple set of things, and you can use that environment exactly over here. And for us, we just charge you exactly on the compute that you use, and we don't care about how many dispatches or how many things you use. And you have an API key that you set on your end, which lets you control it. But that's pretty much it.
Yeah, that's about the gist of it. All apart from the simplifications, the way you work with it is exactly the same.
Yeah, and you get to share your workflows with your colleagues. So if you have a bunch of experiments that you have done, you want to share with, I guess, few has been shared with Radha on our site to look at these things.
Yeah, Will was helping me debug this workflow actually the other day, so.
Oh, that's back.
It's just this one that breaks.
But yeah, so this is how the cloud fits in. So it's essentially the same as OS, but instead of spinning up your own compute resource, you just ask us to do everything on your side, and you don't worry about the infrastructure at all. You just write your code in. So I guess.
Yeah, I mean, in the example I've been running in the open source version, it does look quite convenient and quick actually, but that's because I spent like a day and a half writing the Terraform script to like set this up for me. In the cloud, you would not have any of that. If you want a GPU, you just ask for a GPU and you get it. You don't have to worry about any of that stuff. And this also finished, by the way. But yeah, and then what I've done is, so I stored all the dispatch IDs in the dictionary here. I also printed them out just in case I end up closing this. Then completely independently, whenever they're ready, I can ask to get result, and I can loop through them and print out everything. I'm not going to go through all these again one by one, but here's some cooler images, I guess. Pablo Picasso. This is like Lenin and Mona Lisa put together, this one. Rene Magritte. Do you guys know Magritte? The guy with the pipe, painting of the pipe? Surrealist painter, no? Okay, that's all right. His style is very much like this, but less funky and
That's creepy.
These ones are from the Wikipedia entry for the inland taipan, which is, I think, the most venomous snake in the world. It does not look like this. It doesn't look like this either.
Yeah, Radha is known for knowing a lot of intriguing facts.
some chinchillas, some nightmare chinchillas, vampire squid, ghost Batman, Henry Cavill after a horrible accident. Okay, well, I guess we can. This is all. So this will be all in the repo.
Yeah, can take a look at it, run it again.
Yeah.
But this is a gist of what Covalent is and how people have been essentially shipping compute code outside of their local execution. Yeah.
Is Covalent Cloud a commercial product, or
Yeah.
is it part of the open source?
It's built on top of open source on our end, but you can just sign up and you can start using it, and you just pay for the compute on our end.
So there's not like a monthly pricing that goes to Covalent as well as the compute source. It's just you.
So the price is we do have a subscription and then orchestration fee on top of it, but the compute is purely on your end, so we don't upsell the compute or anything on it. Yeah. But open source is open source. You can contribute it. This Hacktoberfest is done. I guess it just ended probably,
Yeah,
but we had good issues on Hacktoberfest as well. But yeah, any questions, any comments, thoughts? Perfect, awesome then. We have a booth downstairs. If you guys want to meet and chat, let me know. See you guys then. Thank you.
Thank you very much.